Welcome to CS 532W. I'm your friend and teacher, Frank. This is still UBC, and it's still graduate probabilistic programming. Okay, so we're at lecture 14. I think this is frighteningly halfway through. Is this halfway through or slightly more than halfway? More, thankfully, yes, because I'm terrified of having to write the rest of the lectures for the course. Anyway, so we've made it quite a long ways. You should be very proud of yourselves. There's a lot of stuff that's come at you, and there is still going to be more. The pace of info is not going to change, but things should get a little bit clearer as we go. So where are we? Lecture 12, 13. We've done evaluation-based inference. We talked about a bunch of strategies now. Important sampling, lightweight metropolis Hastings, black box variational inference, and we really went through finally slowly enough that I hope the variational inference thing makes sense. And hopefully homework 4, which you all are probably working on right now, should be relatively doable. Okay, so this is, like I said, we've made it somewhere. It's pretty cool, right? It's the end of part 2 of the course. And actually, we've covered a huge amount of territory. And maybe more to the point, we've established a vocabulary to talk about lots of interesting and important things, right? So we've talked a lot about a first-order probabilistic programming language and said that, there's systems like STAN that are equivalent to it, or bugs or whatever, because basically models built in this, modulo the control flow considerations, correspond to inference in a graphical model. And from lecture, what we've talked about in the course are, non-standard we've talked about non-standard interpretation. In other words, what does a program expression mean? So this program means some conditional distribution. We talked about evaluations, in particular implementations of standard and non-standard evaluators. And we've covered a bunch of different inference algorithms. Metropolis Hastings, important sampling, black box variational inference, and Hamiltonian Monte Carlo. And from the homework, you've implemented a bunch of systems, but I mean, one of the things that's complicated in a course like this, and I'm open to suggestions in subsequent years or whatever about at the end of the course, or even after the lecture today, about the ways to sort of reinforce this. But this is a graduate course about probabilistic programming. It's not a graduate course about the use of probabilistic programming systems. And there's always a tension. Like, I could teach a graduate course on the use of probabilistic programming systems and how to frame problems as inference, and how to then use probabilistic programming and the tools of inference to solve problems. But that's not what this course is, right? This course is about building probabilistic programming systems, so that you understand how they work. And should you wish to work on probabilistic programming as a research area, you can. Should you wish to work on your research area using the tools and thinking, related to Bayesian inference or non-standard interpretations of programming structures, you have both the practice and understanding of what those things mean. But from the homeworks, I get the impression, having looked at the work that you're doing and the questions that are being asked, and frankly, some of the facial expressions that I see during lecture, that the use and applicability of the tools that you're building, or the tools that are built using the principles that you're learning about, is something that might be starting to slip away because we're in the weeds so much, right? But let me emphasize again that, in the homeworks, you are solving Bayesian neural network problems, right? They're small scale problems so that you can actually compute in those. But if you are worried about how to express, uncertainty through deep neural networks, you've not only learned about a language or a method for specifying such problems, but you also have implemented general purpose inference engines that allow you to solve such problems, right? Now, you'd be hard pressed to convince me that you can't think about or aren't aware that, properly capturing uncertainty in deep learning isn't a serious problem, right? So we're not focusing on that problem. We're focusing on how to solve that problem amongst many other problems like hidden Markov models. And you're not going to convince me that hidden Markov models are not useful and they're not widely applicable, right? And we talked through many example applications of those, right? Your systems are solving HMM problems. Your systems are solving Bayesian Gaussian mixture model problems. Your systems are solving all kinds of things, right? So let's let's not forget that a compiler's course or a programming languages course or a data structures course or any of these sorts of things, like there's always this disconnect, right? You learn how the tools work, you learn how to implement the things, so on and so forth, but the applicability, it often rests on your shoulders, right? And that's certainly the case in the design of this course. In other words, I expect you to be thinking while we're going through this and sharing the pain of implementing these systems. I expect you to be thinking about, oh, look, we're doing Bayesian neural networks. It's the largest workshop at NeurIPS, Bayesian deep learning, right? And we have a set of tools and techniques that allow us to address this problem, right? We're talking about building the tooling. But let's not lose sight of the fact that the homeworks are meant to be, in particular the problems that are selected for the homeworks, despite them being small, they're meant to indicate the kinds of things that you can do. Ryan, what's covered in Stats 520A?
It's just Bayesian analysis. It's with Alex Bouchard-Cote, but he implements all of the examples in Blang, which is his own Prob Prog, PPL. And like you can do the project in that PPL. Like all of the examples of Bayesian analysis are in PPL land.
So I would be willing to bet, based on what I know about Blang, that unfortunately you can't do a lot of the deep learning stuff, and you can't do a lot of the control flow stuff, right? So I would say that, like in the Andrew Gelman style of solving statistics problems, which also corresponds to what we've gotten through in the course so far because we're dealing with first-order probabilistic programming languages, yes. We could have I don't know why you would do it in Blang. You would just do it in Stan because that's what you should. That's really what you should use. That's the language. So like you now know how to implement Stan and understand more about the language design of Stan than actually the Stan designers do at this point. But if you were to go off and actually solve problems, right? You would use a probabilistic programming system, probably not your own. But if you wanted to go work at the company that supports Stan, you would need to know the stuff that we're talking about here. And you will be a better user of Stan because you have experienced what it means to build such a system, because you understand how it works in a more fundamental way. Okay, great. So that's the end of part 2. Part 3. We're still one part away from getting to the really fun part, for me anyway, and probably for all of you. But we have to go through this next level in order to really get all the way. And the part 3, and what we're going to talk about now, is HOPPL language and inference, which basically corresponds to, again, implementation level considerations in probabilistic programming, where if you want to build systems and you want to understand what the limitations of current deep learning, deep probabilistic programming systems, then you have to consider the things that we're going to talk about in this section, which are complications that arise from I/O and recursion. And the TLDR of this lecture is that basically real probabilistic programming languages, in particular the current batch of deep learning systems, deep probabilistic programming languages, are coded. Model specification can be done in the language, whether it's Python or C or whatever. And those languages share the common complication that is evidenced by what we call the higher order probabilistic programming language, which is unbounded recursion and branching on stochastic on random variables, the values of random variables, these sorts of things, which means that we have to actually think about how to deal with these complications. Now, the fun thing is that inference, some styles of inference are still possible. So importance sampling, which you're going to look at in homework 6, sequential Monte Carlo, which is a super powerful inference algorithm, which we'll talk about on Tuesday, will also be the subject of homework 6, and lightweight metropolis Hastings, which is in the book, but we're not going to cover. So really, what we have to do is, instead of having this silly language for specifying probabilistic programming, probabilistic programs, in which if I asked you to solve problems, you would run into problems, solve interesting AI problems in particular, you would run into all sorts of problems, even specifying the model that you would want to in the first order language. Once you use higher order language features, then you run into some complications. Then part 4, which will come after this, which should be relatively brief in comparison to parts 1 and 2. Part 4 will be about amortized inference, which is where we start thinking about stuff that's relevant to sort of modern approaches to probabilistic AI, basically. And we'll talk about inference compilation, we'll talk about variational inference with guide programs, meta learning, and RL as inference. And to be perfectly frank, unless you're really into the probabilistic programming nitty-gritty, it's in here where I hope more of the course projects arise than necessarily with the nitty-gritty in the probabilistic programming space, although that's up to you. Okay, so today we're just going to talk about HOPPL, and the learning goal is to understand how a higher order language interpreter works. Okay. So unbelievably, actually, and this is somewhat counterintuitive, particularly for those of you who don't have a strong programming languages background, unbelievably, the HOPPL grammar is actually simpler. The grammar, you should be familiar with this now, the grammar consists of variables, check. Constant values are primitive operations. Now you should understand what this is, check. In fact, the grammar technically also includes procedures, but for reasons that we'll discuss in just a second, we don't have to deal with that case either. And an expression now, in other words, the denotation of a conditional distribution, just like we had in the HOPPL case, is recursively either a constant value or primitive operation, a variable, an if expression, a function application, sample, observe, or now this thing, which is an anonymous procedure call. In other words, a lambda, if you're familiar with Python lambdas or lambda calculus lambdas or whatever. So in other words, now functions become first-class objects. Now, how many of you have implemented an interpreter or compiler for a language with first-class functions? Okay, 0. Okay, so I promise you this will be one of the most mind-warpy things you do when you do homework 5, and that it works and is a thing it's incredible, right? It's super cool. So this looks super simple, but this is a much more powerful and much more expressive language than the HOPPL. Okay, so I think the key point is down here. Any of the modern systems, Pyro, PyProb, Turing.jl, Gen, whatever, all of them have model specification languages that have features that cause the same fundamental difficulty that having first-class functions has. And I think you'll be able to see in just a second. So the first thing that you should ask when you see this is that you were familiar before with there being a let special form. And the question is, where did let go? Okay. So let is now syntactic sugar, okay? And I should point out that Daphne supports, so Daphne now, when we talk about this, will support desugaring of the higher order probabilistic programming language, so that any program that we write, you will end up seeing in a form that only has these. But now the desugared expressions from Daphne are going to be rather confusing to look at. Okay, so you should just be aware that this is going to happen. Okay.
Sorry, can I quickly ask something?
Please, absolutely. Yeah.
Yeah. So I remember that, like, for the first order, like for HOPPL,
yep,
you ensure that, like, the program's gonna stop eventually. Do we have that
No,
here? Okay.
we do not.
That's gonna be fun.
So, but this is precisely, this is an excellent point. And this is precisely the point of when you have a full Turing complete universal programming language, you can write programs that don't halt on all inputs, right? So now we have this to deal with, which means that we cannot at compile time certifiably unroll the program into a graphical model. Period. Not going to happen. So you'll notice that there's no like Gibbs sampling or whatever inference engines that I talked about on the previous slides, right? All we can do are evaluation-based inference, right? Yeah, approaches. So let's desugar away let. So Daphne, you're gonna see standard programs. You'll see the test programs in the Bootstrap code for homework 5 that look like standard, Anglican /HOPPL programs. But even if you take a HOPPL program and run it, so first of all, you can take any HOPPL program and you'll be able to run it in your interpreter. But what will happen is that it will get desugared very differently. Okay, and it's going to get one of the first things that will happen is that let gets desugared in this way, and I want to make sure that you see what this means, right? So let x be the value of E1, bind the variable x to the value of E1, then evaluate the expression E2, right? Well, this gets desugared into an anonymous function whose syntactic argument has name x and body E2, and this anonymous function is applied to the value of the expression E1. You can see how these two things are equivalent. Yeah. So that means, oh yeah, and I should point out, just to be clear, oh, I guess this function, we do have functions of multiple arguments, but that's fine. So so this let block here first desugars in the standard way that you're familiar with from the FOPL, which is to say that it gets desugared into a set of nested let statements with single bindings, including introducing variables. This would normally be a fresh var here, but it doesn't really matter, it's just some variable c here. And the result of this let block is the value of times AB. Note that k, in the way we were talking about it before, is a free variable, right? Okay. This gets desugared to this expression. Okay. So the first thing that would happen is that plus k2 would be evaluated, right? Then this thing would be evaluated, which is an anonymous function that takes a single argument, which is a, and does something to it. And what does it do to it? It multiplies a by 6, and then supplies that as an argument to another anonymous function, which has a single parameter named b, which does something to basically. So you basically recursively apply this rule, and this is what you get at the end. Okay, so it's a bunch of nested anonymous functions, right, that are applied to arguments computed from the the bound variable names. Payment, you're thinking or have gas or something?
I'm just thinking.
You're good with this. Everybody's good with this desugaring. Okay. So this gets rid of. So who cares? We could put a let expression in the interpreter, but that just means you have one extra statement in your interpreter. You don't want to have a case to deal with in your interpreter. You don't have to deal with that. So we just have anonymous functions. That's it. So we get rid of let. No let. Awesome. But given that we have anonymous functions, we can do some nice things. So loop, which we had as a syntactic construct that got desugared away, now will be desugared into something entirely different, right? So loop will be desugared into a let. So if I did the full desugaring, you would never be able to see what's going on. It gets desugared first into a let block like so, in which an anonymous function is created. So there's a bound, there's an initial value for the loop, there's a bunch of argument values, constant argument values that get evaluated. And then there's an anonymous function G, which takes the loop index and of an accumulator variable W, basically, which applies the supplied function F. Now F is a, is a first-class object, right? To the value of I, the value of the accumulator, and the fixed values of the arguments, and then calls a function loop helper, starting with the starting index with, I guess the bound is W, excuse me. Yeah, where did W come from? Oh, yeah. Yeah, bound is C. Sorry, that's not an accumulator. The initial value, which is the value of the initial expression, and this function G. And what does loop helper do? Well, it is a recursive call that actually implements the loop. So if I is equal to the bound, then return the accumulated value V. Otherwise, call G, which is again this anonymous function, at the current loop bound with the current accumulated value, keep that around, and then recursively call loop helper with an updated index, so on and so forth. So basically, what it does is it takes this function, which is the body of the loop, and recursively calls it. Yeah. In other words, the fun thing is now this bound no longer, this loop C here, no longer has to be a constant. So we can really look at this in a couple of different ways, and I think it would be better to actually see it like this. This is going to be an expression, and this can be an expression because that will get evaluated at runtime rather than compiled. And also, just to be clear, I said we got rid of def-in, so this is going to make you a little bit uncomfortable seeing a def-in here. So let's just say, and hopefully this will make sense and you'll remember it, there will be an outer context which will be provided for you always, which has a let in it, which has a loop helper in it, which is an fn form like this. And then this will get closed and your program will be in here.
Can I ask a question?
Please, yeah.
So what is the difference between fn and def-n?
So def-in was a syntactic construct that we used in the HOPPL in order to have function call-like semantics. So basically, by specifying a block of code that we could rewrite in, we could make it appear as if you were doing function calls, right? It looked like a function that you could call. Fn says create a function typed thing, Like it is actually a function that you can pass around. So there was no way you could pass around defined objects. Like if you remember, the set of f's could only be used in the position of function application. So in the HOPPL grammar, the only place that f ever occurred was in this position in one rule, right? In this, and again, this is, you have to be somewhat comfortable with functional languages, right? Any one of these expressions can be a function, which means that you can pass function valued things around, including to themselves. Okay. Okay.
Can I ask a question as well?
Yeah, please. Yeah.
Is defn, is it like 100% syntactic sugar, or is there some like semantics to it that are not completely captured by fn?
Nope. So like in the reason why we can desugar all defns, if you look at it, this is just like we kept this the same so that you can take HOPPL programs and run them in the HOPPL. Sorry, other way around. HOPPL programs run them in the HOPPL. But if you think, basically this allows, defin, whatever, block, program,
Mm-hmm.
right? But this whole thing can trivially be desugared into, let whatever this name is, A be fn, B be fn,
yeah,
program. And then that let block gets desugared and then into anonymous functions, and you're off to the races, right?
yeah, okay.
So when you saw me earlier in the term say, Christian, desugar the HOPPL so that it doesn't have any defin forms, he was like, oh, okay, yeah, no big deal, right?
Yeah, okay, gotcha.
Believe it or not, I'm actually trying to be nice to you all by eliminating cases that you need to implement in your higher order interpreter. I know it seems unlikely, but this is about as minimal a language you can. If you think about it, we've got function application, functions, constants, and if. You don't have a much smaller language than that, right? That's all you have to be able to interpret. Right?
Can I ask another question?
Please.
So just going back to when I asked before, what makes it higher order? It's higher order because functions are objects now? Is that
functions are first-class objects, and functions can call themselves.
okay? And so that's why we couldn't have fn in HOPPL, because functions aren't first class.
They're not first class, and they couldn't call themselves. So there's no general recursion.
Okay. Thanks.
Was that a hand? I mean, oh no.
You just answered my question about general recursion.
Okay, cool.
Yeah, thank you.
Mm-hmm. Okay, cool. All right, so I think the take home from this is you're going to see desugared programs that are going to look totally insane when they come in, right? And there will be stuff in the environment like loop helper and all sorts of stuff, right? The power of these sort of anonymous functions, and again, you should really think all of these are going to be desugared into a let binding with, where these are just named lambdas. But the power becomes a little bit more apparent when you start thinking about higher order language features like map, reduce, and repeatedly, right? So you will see some of these show up in your programs, and you can write with these. And once you actually have these in your arsenal as a programmer, which many of you probably do not, unfortunately, but they're relatively straightforward, right? So map, what does map do? If you have a collection like 1, 2, 3, 4 as a vector or whatever, and square, and as in the mathematical operation, square is an anonymous function. So you could write let square be fn x times x, done. And then you write map square of this. This will evaluate to 1, 4, 9, 16. And you can see this by just seeing what's going on here. It's like, if this is a recursive procedure which bottoms out on an empty collection and creates a list, and so the recursion is it sticks together an application of this anonymous function f to the first element of the collection and then recursively maps f over the rest of the collection, right? And then joins those lists together, right? So reduce is another incredibly powerful, so assume that we have a function called sum. So if, well, I guess you just do reduce plus, never mind. Reduce plus, so plus is a first order, like we can treat plus as it's a function, right? It's take as a function of 2 arguments, right? So if we do reduce plus 0, 1, 2, 3, 4, right? This will return 10. And you can see what this does, right? It recursively calls itself by applying the function with the accumulant on the first of the collection. So this would be plus 0, 1. And then this is now the accumulated value, 1, and it recursively calls f on the rest of the collection, which is 2, 3, 4. And the next application will be f of 3 and 3, 4, and so on and so forth. This would be reduce, and f in this particular case would be plus. So you can implement sum, right? So if you want to sum a collection, right? So you can do something like let sum be fn x reduce plus 0x. Okay. If you want to make a vector of some length repeatedly, right? You just if you want to repeatedly call a function. So if you want to create a vector with random elements, normally distributed normal 0, 1 random like a normal 0, 1 vector, IID normal 0, 1 vector, you could call repeatedly 10 fn with no arguments, sample normal 0, 1. And what will this do? Well, again, it's a recursive procedure, so it will put together an application of this function f, which is, if it's an anonymous function that samples a normal random variate, is going to just generate a random normal variate, and then stick that together with a repeated call n-1 times of the same function. So this will make a normally distributed. So this right here is a normal 0, 1 vector where every of length 10, where every vector is normal element is normal 0, 1. Okay. So basically, looping and recursion, you can basically you should know that you can write any looping procedure via recursion and yeah. So once you have functions and you can do recursion, it's a matter of thinking this way. So this is like thinking recursively, whatever. And again, we're not saying, this is the critical part, we're not saying that you should abandon all the programming languages you've ever known and start programming in the HOPPL, right? That's not the point, right? What we're saying is that if you want to use probabilistic programming, if you have a problem that you understand how to frame as Bayesian inference and you want to use a higher order probabilistic programming language with normal language features, you know that under the covers it has to be doing something like this in order to implement things like for loops that have bounds that are evaluated at runtime. Okay. And we're not talking about stack machines. We're talking about, scheme interpreters. And that's fine. The critical part here is the data structures are like whatever these like map is and whatever these collections, you don't have to tell the system the length anymore. So you can read these in, or you can get them from the internet or whatever you want. And that's the other bit, right? Because you now don't have to actually pre-specify the lengths of everything, right? So that's the first thing, right? So like everybody was really weirded out by the fact that you had to inline data and basically recompile every single time under the HOPPL. Well, under the HOPPL, that's clearly not so. So you've been looking at hidden Markov models, but the way the hidden Markov models you were looking at, they always had the data inside a let, right? Which isn't so bad if you write the program programmatically. But here you can actually develop modular stuff, just like you would want to as a standard programmer, right? So there's some function which reads data from disk. We don't know how long the data is, right? And the point is now you can write an HMM in this way, which uses the function reduce that we just talked about, which takes a function and an initial accumulant and applies it and reduces a list, right? So we assume that the read data is a list of data of unknown length. The accumulant starts with a sample of the initial distribution, which is just a sample from a discrete distribution, right? And an HMM step, which takes transdis and obsdis, which again, we can sample these at runtime. We don't have to know how big they are. You can have unknown state cardinality HMMs because you can sample the number of states and then sample the transition distribution from a prior and so on and so forth, right? HMM step is a function that takes these transdis and obsdis and returns an anonymous function which closes over those, and that function takes a list of states and a list of data and basically does the reduction. So it pulls the state, it generates a state from the last of the state sequence. So this is going to build a list of state sequences as it goes, and the last one of those will be the last state that the HMM was in. So that's last states, that's this right here. Then it observes by getting from the observation distributions, which it's closed over, these things, indexed by the newly sampled state, the given data item, right? So remember that reduce is going to pull an item off of this list of data, which might be, whatever, 1.7, 3.4, whatever this, something like this, and call this reduction function, which takes, again, the accumulant and one element from read data. So this is going to be one element from read from this list out here, and then it conjoins onto the state. So the accumulant is actually accumulating it's adding on to this vector. So now we have a completely generic, completely encapsulated HMM, right? So this means this is actually the meaning of HMM. And because we don't have to do anything at compile time, really, right? You can make this stochastic with an unknown and potentially unbounded number of elements, right? In other words, it can also be stochastic in this direction if you want, right? So specifying Bayesian nonparametric models, which not many people talk about anymore, but are still conceptually very, very beautiful, is incredibly straightforward. Or what's his face at Berkeley, my friend Peter Norvig and Stuart Russell. Stuart Russell would call an open world model, and I think we have one of those next, right? So the open universe mixture model. There we go. Okay.
That's good. Quick.
Yep.
A sort of tangentially related question.
Yep.
Why is it called a hidden Markov model? What's hidden?
Because this has this graphical structure, just like you've seen. So these are hidden variables or latent variables, and these are observed variables.
Okay, thanks.
Okay. And again, just to remind you, these could be words, and these could be parts of speech, or these could be, I guess technically they would be tokens, and these would be parts of speech. So like noun, verb, whatever, and there would be words here, or this would be a bunch of Mel-Kepstrel spectrums, and these would, and the hidden variables would be the phonemes. Or for Vasilios and Payman, these could be, the bottom would be observed vehicle positions, and the latent variables are driver intents and goals, and emotional states or whatever for drivers. Yeah. Okay. So again, thanks to Stuart Russell for this. This is an open universe mixture model, and we'll start to see where this unboundedness again matters, right? So when you're doing mixture modeling, right, the classic question is, how many clusters are there? I think Namrata actually even asked this earlier in this class. It's always the question. Every time we talk about mixture models, it's always a question. How many mixture components are there? Well, wouldn't we like to be able to do inference over that, right? Okay, so here's one way to do it. Here, again, we don't have to close over the data, but just for this purpose, we've closed over the data. This is interesting. So we can sample K from a Poisson distribution, for instance, right? And now things get really interesting, right? So we've got this repeatedly function, but now we're going to repeat some potentially unbounded number of times. So where did, oh, there you are, go. Everybody switched around. So like Ina said, we have a potentially non-terminating computation here, right? Poisson, it has support on positive infinity, right? So this could actually not terminate, right? And in fact, this data structure could be infinitely long, right? Same thing for so that means that the prior on the class identities for the elements here could be who knows what, right? And the likelihoods also, where now we have some sort of prior on an unbounded number of likelihoods. Right? And we can map this anonymous function, which samples from the Z prior, which again can be unboundedly large. And we can observe under the nth, which can be unboundedly large component. We can map this function, which is a function of y. We observe y over the data, and this is the data, okay? And what it does is it returns Z in each of these instances. So it would return the class identity for every data point, but there's an unbounded number of classes. So this will automatically consider all possible mixture models up to and including a number of mixture components that is as large as the number of data points. And your question, which you've asked before in the homework of like, are these two data points in the same class, will now average over not only the mixture components, but also the class cardinality automatically, okay? So again, whether or not you fully appreciate what you see here, and maybe you have to take a whole lot more classes, or maybe you never will, who knows, right? But when you start thinking about non-parametric Bayesian or open universe mixture models for whatever reason, or determining class cardinality or whatever, you could ask for the class cardinality at the end if you wanted to. Like having a facility that gives you the ability to actually frame and answer questions like this automatically is magical. It's really, really powerful, right? And unfortunately, though, this means that you can't do the HOPPL thing. You can't unroll this loop at compile time. It's not possible, right? Fine. And this is just, yeah, go ahead.
In programs like these, for example, with like a Poisson distribution, like, can you get an unbiased estimate of distributions if you know that you can never terminate a program if you you accidentally sample infinity for your Poisson? Like does it mathematically work out?
This is a really, really deep and interesting question, actually. What do you do with probability? What do you do with the probability mass of non-terminating executions? And there's probably 500 papers that have been written on the subject. And if I'm perfectly honest, it's the reason why I'm at one of the reasons why I'm at UBC is that David Poole works on this subject quite a lot. Actually, it's something that he's very, very into. And in this model, you'd be okay because you could show that like the number of non-terminating executions, like the number of them and the probability of them are such that this converges to zero. Basically, you don't have to worry about it. However, there are lots of other programs, like for instance, this kind of program, in which it is very, very, very easy to construct models in which a substantial fraction of the program execution traces do not terminate. In which case, the semantics of the program become exceedingly complicated to reason about, right? So there's like deep mathematical things that I ask my deep mathematical friends to solve, right? Because they're tough. And I'll try to point this out. So early on, I said like, cool, let me give you a challenge problem, right? And if we started the course with this, please do program induction for this particular for flash fill in Excel or for doing symbolic regression. I am 100% certain that none of you would be able would have been able to frame the problem or write down a solution for it, right? And we could spend the entire course talking about how to do that. But we're getting to the ability to do that in a completely different way, which is we're going to give you the ability to solve arbitrary problems of this form, of this recursive form, which means that, for instance, doing symbolic regression and program induction symbolically is within the remit and your ability as soon as you can write in a language like the HOPPL, okay? And that's pretty astounding, actually, right? So I'm saying by the end of homework 6, you can do program induction. You might choose not to, or you might choose to do it in a language that you didn't implement yourself, so it's fast. But if you're interested in program induction, you can solve such a problem. Done. Just write it down. Okay. So what do I mean by this? Just to remind you, right? There's this. This problem of like, give me a regression function expression given data. So I'm going to give you some data, and it doesn't have to be in 1D or 2D or whatever. So it's not arbitrarily stupid, but I'm going to give you some data, and I want you to give me a symbolic expression for the regression function, right? So maybe you're in healthcare and you really want to have an interpretable regression expression that a clinician can look at and say, if diabetes is over this and BMI is under that, and so on and so forth, you're going to have a brain tumor. I don't know. I'm sorry if that's triggering, if anybody has had a brain tumor or knows anybody who's had a brain tumor. But so how does this work? This is going to be a list of ins and outs. Again, these are going to be ins, these are going to be outs, right? The critical part is this. Let the function, so this is going to be a prior B, generate an arithmetic expression. We're going to generate an expression, okay? So what happens here? Well, this is the function generate arithmetic expression. Read this as a def in, which that you can sugar away. That's no problem. Sample an expression type from some discrete distribution, and then switch. This gets desugared into a nested set of ifs. It's just a conditional expression, right? So if the expression type is 0, then sample from a uniform discrete distribution over 0 to 10. So you're only allowed integer values 0 to 10. If the expression type is 1, sample the symbol x. So I'm not making you implement quote, but honestly, it's not that hard. You could do it. Otherwise, let the operation be some operation. So generate operation I haven't put on here, but this is just going to be another stochastic function that returns some one of times, plus, divide, whatever you want, sine, cosine, doesn't really matter. And then you construct a list of the operation, which is going to be a symbol, and then a doubly recursive call to generate expression. So this samples from a program grammar. In other words, you could read a paper that I wrote with one of my students at Oxford called Ura that literally writes HOPPL programs. Like you can generate HOPPL programs, right? It's no problem, right? So this is going to generate some expression like plus, x times x2 sine whatever. Okay, so I guess these are all binary expressions, so sine is out. I apologize for that. So let's put, divide 10. So the space in which we're going to do inference is in the space of these function expressions, right? So now we're going to loop. This is again going to be desugared into all of these anonymous, like the loop and loop helper, and then the lets and so on and so forth. So you're going to get an enormously complicated program expression at the end of the day. We're going to loop over the ins and outs. And what we're going to do is we're going to observe a noisy eval of the func, which is a symbolic thing, on the first element and the outside element. So this is just basically an ABC likelihood or approximate Bayesian computation likelihood, where you actually have an eval function written as well. So, but you know how to write an eval function because guess what? You have written eval. So you can write eval in your language. Okay. In particular, you can only write eval in the HOPPL. Okay. Cool. So this is Anglican code, but it doesn't really matter. You should be able to read this code at this point. Yeah. Okay. So language design considerations. So IO versus inlining. Now in HOPPL land, you're allowed. Basically, I should say, when we're thinking about PP language design considerations, right? If you do IO versus inlining your data, then you're in HOPPL land. If you think about writing a program, if you're like, dude, Frank, your HOPPL and FOPPL languages suck. I'm going to write my own because I think probabilistic programming is awesome, and your language design stinks because I know that I can do, IO in FOPPL land. Nope, you can't. If you have unrestricted IO, you're going to be in HOPPL land. So you got to do what we're going to do now. If you allow dynamic loop bounds, right? If you allow runtime determined loop bounds, nope, you're in HOPPL land. If you want higher order language features like map and reduce, you require dynamic computation graphs, and that puts you in HOPPL land. If you use an unmodified existing language like Python, Julia, C, C++, Clojure, Java, blah, 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 as a modeling language, this requires HOPPL inference, right? And again, these are the things that you can do. Maybe you can do BVI, maybe you could do Hamiltonian Monte Carlo. Their correctness is not established yet formally, as far as I know. And in particular, and this is something that my group has done a lot of work on, if you have models in the form of stochastic simulators that are written in some language, whatever that language happens to be, and we've done some work on epidemiology for multi-agent Fred simulation, and we've done some work in higher order physics where we use the simulators as a standard model in the Atlas detector particle detector, which we talked about in the first lecture, then you're in HOPPL land. You have to deal with all the stuff that we're going to have to deal with. Yeah. Let's do a break until 4:30, and then we'll get going. Okay, welcome back. Okay. So we've got a pretty hefty chunk of stuff to get through. So So HOPPL programs also denote joint a joint and conditioning, right? That's it. You can forget this line. You don't have to worry about this line, but there's a program. This is also a HOPPL program. It's also a FOPPL program. But when you think in HOPPL land, you really have to be thinking evaluation-based. And you've already got an idea of what evaluation-based is. You know that like you generate a sequence of observe and sample statements at runtime, and you evaluate the probability of a trace, right? So halting executions of a HOPPL program generate a sequence of observed sample statements at runtime, right? And you really can think of this, and it's not inappropriate at all to think about this as some state space model where the latent variables are the, increasing subsets of program execution states, and the observed statements are the observed statement. So in some sense, you can think of a HOPPL program or evaluation-based inference as kind of a generalized Markov-like model, right? For a statistician, they would just say this is a Markov model. Okay. Just to make this, I'm going to skip over this, but this is this is another example from the very beginning where you generate a tree, and in fact, like inside of a HOPPL program, you can write rejection sampling within the HOPPL program, right? That's kind of interesting to think about, right? But the trace probability is just the joint distribution of all the random variables and the observes, and you can think of them as in this kind of state spacey style way. But this simple sketchy notation hides a complex branching dependency structure. In other words, basically, these x's in this bold case case are subsets of random variables, and that means that basically x6 depends on everything to the left, and x5 can potentially depend on everything to the left, and even the type of the random variable will depend on. So this basically says the type of the random variable, the parameters of the random variable, everything is deterministically computed from the previous values of the latent variables plus the whatever the code is in your simulator. And that's the same thing is true for the observation distribution. So the type, so this could be normal or gamma or whatever. The type is a function of the latent variables in the program. The parameters are a function of the latent variables in the program, which is going to be dependent on control flow, everything, right? So this just joint distribution hides a crazy amount of potential connectivity, right? So we've got a sequence of n observed, sequence of m samples, blah, 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 and condition on these sample values, the entire trace is deterministic. That's important. Okay. So how do we implement this? We can do it in there's like two big ways of doing it. You can interpret in the way that we've been doing, and that's what we're going to do in the homework. You can interpret such a program, which requires you to track side effects and direct control flow for inference. Or, and this is, I just want to put this in front of you so you're aware that this can be done because it's pretty cool. Or you can do this in the sort of a traditionally compiled way, where you can actually do inference where you only exert control over control flow from within function calls. In other words, you can leverage existing infrastructure and so on and so forth. And this is actually how modern probabilistic programming systems are built. Doing this in homework would be too much. Doing this in homework is tolerable. But in order to do this, which you're not going to do, but I'm going to talk about for just a little bit right now, you have to actually know about a couple of other things, which are pretty cool. And these are continuations and immutable data structures. They're required for sequential Monte Carlo. They're required for efficient Markov chain Monte Carlo. And if everything I talk about in terms of continuations and immutable data structures is uncomfortable for you, then if you're familiar with POSIX fork, you can think about POSIX fork instead. Yeah.
So we're not going to use our base code for previous homeworks for homework 5? Because it was a compiler, right?
No, you're not going to write a compiler for homework 5. You're going to write an interpreter.
But for homework 3, for example, we wrote a compiler, right?
You've not written a compiler. You've written an interpreter.
Isn't an interpreter supposed to like run code line by line?
Correct, and that's what you wrote. A compiler translates code from one language to another language. An interpreter evaluates program expressions to their values.
Yeah, that's right. Yeah, okay. Thank you.
So you've written interpreters in all instances, right? And when you write a compiler in the traditional sense, you're translating program expressions into bytecode that then the machine interprets, right? Okay. So in all cases, you've written interpreters, but what I'm saying is you can use, when I say this implementation bifurcation happens, you can do probabilistic programming using existing compilers that generate bytecode that is opaque to you and can be executed on a machine, and you can still do inference even though all you have are interrupts at function calls, in particular, very, very important function calls like sample and observe. So this is the bifurcation. So at this point, it's like every time we do this course, I try to decide which way to go, but I think this is the only way to go, unfortunately, in a course. We could go 4 different ways. We could write a non-standard evaluating interpreter, which builds on homework 3 and reuses your effort maximally. So that's what we're doing, right? This will require you thinking about pure data structures for use of sequential Monte Carlo implementation, which is homework 6, and is very closely related to the Anglican paper that I wrote a long time ago. Or we could do continuation passing style transformation and within language control. So in other words, we could use existing compilers via sample. So there's lots of information on this. There's a really excellent resource called DIPL, the Design and Implementation of Probabilistic Programming Languages at Stanford, which is very similar to what we did with Anglican. And this is actually how Anglican is implemented, and that makes it super, super fast. We could do OS or virtual machine provided heavyweight coroutines using fork. That's pretty cool. And if you want to see the most hilarious paper I've ever written, Probabilistic C would definitely be it, because basically, as Dan Roy at the University of Toronto said when he heard about Probabilistic C, he said, we're done. Like you have made all probabilistic programming languages, and in some sense, that's true. Or we can do control over message passing interface, and that's what chapter 6 in the book is about. And this is what PyProb is, and it's super cool and allows you to do inference in simulators, but it derails us from being able to talk about some of the more interesting stuff that comes later on. So we're going to do a non-standard evaluating interpreter because the homeworks are doable, basically. But we're going to talk about continuation passing style for just a second, because it's cool. And if you don't know, how many of you have heard of CPS? Okay. So again, this is the kind of thing that you get to be able to do if you have access to the source code of your models. Okay? And it allows you to do really, really cool things. So you haven't heard about this or implemented, it's cool. It's covered in CPS C311, definition of programming languages. Okay. So the point is that a function written in a continuation passing style takes an extra argument, an explicit continuation, i.e. a function of one argument. When the CPS function is computed its result value, it returns it by calling the continuation function. So no function actually ever returns. It only calls a continuation function. That means that when invoking a CPS function, the calling function is required to supply a procedure to be invoked within the subroutine's return value, with the subroutine's return value. Expressing code in this form makes a number of things explicit. This is pretty cool. These include procedure returns that become apparent as calls to continuation, intermediate values, which are all given names, order of argument evaluation, which is made explicit, and tail calls, which simply call a procedure with the same continuation, unmodified, that was passed to the caller. Cool. So there's a whole lot of work on this. So you can write code in continuation passing style, but more to the point, you can take code and programmatically, via metaprogramming, transform it into continuation passing style. And that gives us some really interesting benefits, particularly in the design and development of PPLs. So this is what we would refer to as the direct style. So this is, what does this define? This defines, the x squared plus y squared. These are the same. You would agree with that, yeah? This is just Python code, right? Or not, I guess it's not Python code, it's scheme code, whatever, it doesn't really matter. So this is scheme code. You should be able to read this. This is the function name. These are the arguments. It's a slightly different syntax than we use in ours, but it's the same thing as an FN or defn. Okay, continuation passing style is pretty different, right? Okay, so let's try to read this. So the point is that we can do this transformation automatically. And there's a chapter in the book on this, basically. So what does this do? Well, we define a continuation function that takes a continuation and the arguments. Okay? And what does it do? It first calls a function times this, which looks like this, given the values of x, and then call with a continuation function, which it's given a continuation function. Okay, so what is the continuation passing style transform of times do? Well, it takes two arguments, it multiplies them, and then calls the continuation. Okay, fine. So this continuation function takes the result of times xx and calls another function with the values of y here, and then calls a continuation function, which adds, and then takes the two argument values. Again, these are bound by the lambdas, right? And then calls a continuation function, which is takes basically the result of plus and calls another continuation function on that, and so on and so forth. So if you pass the identity function in as k here, what will happen is that a function will be called, but before that function is called, an anonymous function is created, which is its continuation, right? And in the creation of this anonymous function, another anonymous function was created, which is this lambda, and another anonymous function was created, which is this lambda, right? And more to the point, these anonymous functions can close over these formal arguments. So in other words, they can capture the state of the program that exists prior to the call of the continuation, and they explicitly represent the rest of the computation, which is to say you could abstract this thing out and say, okay, there is a function that I can call, or should call, when I'm inside of times, which is the rest of the computation. Moreover, I could, if I wanted to, call that function multiple times. Or I could choose not to call that function, or whatever, okay? So you should be thinking in your head, if I do CPS transformation in PPL land and I have CPS transformed versions of sample and observe, I can intercept the computation, and because of the source code transformation, I have an explicit representation at that point of the rest of the program. I can just call that function and say, please run the rest of the program. So I've captured, by a syntactic transformation, by a source code transformation, a compilation, an explicit notion of a continuation, the rest of the program. Okay.
I have a small question.
Please, yeah.
So like these lambdas, can they have like more sort of return, like more than one return variables? Because this one, it's like just binding between like the variable name and whatever the result is.
There are no returns in the continuations passing style. No function ever returns.
Does evaluate to something, isn't it?
No. At the end, the very, very last thing is a function which takes a continuation.
Okay.
So that function will call the continuation with its result. So you feed this entire thing the identity function, and at the end, your function k, which you get to define and hand to it, will get the result of the computation up to this point, and then do whatever it wants to with it, print it out or whatever, right?
Okay.
So like literally, they're like this function, this times ampersand, which is basically a way of saying this is a CPS transformed primitive function, a boxed function, right? It doesn't return, it just calls the continuation.
Okay. Then still like these lambdas, can they have like more than one argument? I don't know, like why do you even need like these arguments?
In general, yes, they can. Yeah. Yeah, okay. But you can also, just to be clear, you can also always desugar a program such that lambda only ever takes one argument, because you can always construct nested lambdas that take all the arguments, right? So really the fundamental thing that you need to care about are lambdas with one argument.
Okay, thank you.
Yeah. So I won't belabor the point, but you know, you can always skip that. That doesn't really matter. If you do a CPS transformation, so here's a HOPPL program, roughly speaking, just say, you know, return P, that's fine. That's a HOPPL program. If we do a CPS transformation, And then we can start to look at a few of the examples of what's going on here, right? So if we do a CPS transformation, we know that, like, for instance, this thing takes the result of this computation, right? So when we call our CPS transformed version of uniform continuous, it's going to call a continuation function. When we do the transformation, there's going to be a continuation function that's created, and that continuation function is going to call a continuation transformed version of sample, which takes the dist argument that was created, right? So in other words, uniform continuous inside is going to create a distribution. Normally we return it, but instead it just calls its continuation with this distribution type object, right? And then sample takes a distribution type object and a continuation and does something with a continuation. And what does sample do? It returns a value, right? But that means that its continuation needs to take the value and then do something, okay? And we can go through this all the way. But the point is that we have a continuation passing style transformation of this program where we have access to, in particular, really this is the critical part, we have explicit continuation functions, and we have our probabilistic primitives, which we write in continuation passing style form. Okay, so we transform all the code and we get probabilistic primitives, but even more to the point, and this is where it gets interesting, is that we have the ability to write explicit forms for all of these continuation passing style observe and sample statements. And you could read this as return. Again, it doesn't really matter. Okay. Which means that provided that we write the continuation passing style forms for sample and observe, then when a standard compiler, in the way that Amin was talking about it, compiles this CPS transform code, provided that we provide implementations of the continuation passing style forms for sample and observe, then it will emit bytecode that allows us, this is the critical part, to have our functions called with explicit anonymous functions that we can call for the rest of the computation. Pretty mind warpy if you've never seen CPS, okay? And that means that, in order to make a fast higher order probabilistic programming language, all you need is metaprogramming. That would be convenient, right? Continuation passing style transformation and implementations of the primitives in your language, which again, you can think of this as return. It really doesn't matter. And in fact, if you just want to do like if you want to do a no-op, if you want to sample from the joint in this kind of environment, this is what you would do, right? Sample, the continuation passing style form, would take a distribution and a continuation, and what would you do? You would sample from the distribution, call the sample that you know and love. You would actually sample from the distribution and call the continuation. That just means the rest of the program will run, right? Observe is a no-op. It doesn't do anything. It produces only side effects. So all you would do is just call the continuation. And return would just return the value or call the return function. Okay. So if you ever look inside of Anglican or Web People or Church or something like that, you'll see that this is actually what's happening under the cover. The program is being compiled to CPS form, and then all the inference algorithms actually operate on this interface. It's also how we figured out that we could do something like PyProb, where literally the only interface is across the network, and those network access points are at sample and observe expressions, basically. This isn't the whole story. You still need addresses, and addresses are nastier here because, again, you can have an unbounded number of random variables. So that means you can't give them names up front. You have to dynamically generate the addresses as you go. Okay. And some inference methods require being able to identify unique random variables, important sampling sequential Monte Carlo with variable-specific proposals. And lightweight metropolis hastings and variants definitely require you to know which random variables are what. Addresses must uniquely identify any sample and observe call that can be reached in the course of executing a program. Fine. So the HOPPL address and transform, which we talked about earlier, can't be used since this transformation inlines the bodies of all function applications and creates, and you can't do that here. So in short, in the HOPPL, you can use a stack trace to provide a unique identifier for the current location, basically a call stack to identify a random variable and associate a unique address with each one at runtime. And there's a section of the book on this, and it's worth just seeing what's going on. So this is a source code transformation again, where what you do is you transform the program to be in the form of an anonymous function that you can then call with an address. That's the outer level transformation. Then all functions, anonymous functions, are transformed to take an extra argument. And that's recursively done. But at function application, you modify by specifically writing code that says add to the address something about the function call. So when you make function calls, you're changing the address and providing a unique identifier for random variables as you go by basically showing where you are in the call stack. And every time you generate a random variable, also modifying the address at runtime. Okay. So this will give you, in combination with the CPS transformation and threading state through, basically a glimpse into how all this works. So in actuality, what you do is if you have a HOPPL program, you run an address transformation on it, then you CPS transform it, that gives you your program, then you could shove that through a standard compiler, run it, and the program will escape into your definitions of CPS transformed sample and observe statements. Those will be provided with compiled functions that represent the rest of the execution. And in, for instance, important sampling, so let's see, I hope somebody's getting what I'm saying, so I want to see. So how would you implement important sampling in such a framework? We'll start with likelihood weighting.
So just apply likelihood weighting here to the, what was the sigma?
Yeah, so one way to think about it is that you have a global likelihood accumulator, and every time an observe expression is hit, right, you just keep track of the log weight of the value provided under the distribution provided, then call the continuation. So basically you just add to, you know, yeah, so if there's some global weight, then you just, you know, plus weight log prob d a dist value, call the continuation. If you have proposal distributions, you can actually sample from a proposal distribution and compute a likelihood ratio in sample. You can do all sorts of stuff. Okay. More to the point, if you do, and this is where it gets really fun, if you do lightweight Metropolis Hastings and you select one of the random variables to modify, you can directly jump to that random variable, that address, provided that you keep track of the continuation that's called from that point in the program, and then modify its value and call the continuation. and keep track of state in some sort of global structure. In fact, the way you really do it is you also thread a state variable through the entire thing so that you have a local variable that you can mess around with. But again, we're not going to do things that way. What we're going to do instead is eval. And I have 2 minutes to explain the evaluation of higher order language program expressions. So see how this goes. So you already know eval from HOPPL, except that you didn't have to deal with the FN form. And the reality is that there's really no way to understand higher order language interpretation without implementing an interpreter. And even then, you'll get it to work, but maybe not understand. And then in a year or two, you'll be like, oh, that was really crazy. That's cool. This is it. And unfortunately, I'm not going to be able to do this in 2 minutes. That's pretty clear. So I'll do a little bit, and then we'll start with this at the beginning of next lecture. Actually, I think what I'll do is I'll do this instead. I think you'll be more comfortable with this than with the SICP notation. Then we'll go back and do the SICP notation. So yeah, I'll do it in this way. So as part of homework 5, I strongly suggest that you take a look at Peter Norvig's Lispy implementation of Lisp in Python, because basically that's the same as homework 3, modulo the fact that you haven't dealt with FNs. So you're comfortable with having an environment. You've already got one of those from homework 3. It basically is a definition of all the primitive procedures in your language. You're comfortable with an evaluator, right? You already have cases for variable references. You have cases for constants. You have cases for conditionals, so on and so forth. But what you do not have is lambda or our FN. And the notion of there being a primitive procedure type says that if you arrive at, and this would be FN in our case, if you arrive at an FN, then you have params and a body, and the evaluation of a procedure, of a lambda, returns a function type object, which is a procedure which consists of a list of the parameters, the body, and a capture of the environment in which the procedure was defined. And that part is the part that trips people up. Because when you define an anonymous function, it binds values of all of the variables, all of its free variables in the environment. Whatever's in scope, it takes those values. Okay. That's fine. And yeah, so that's the
Can I ask a question?
Yep.
In our previous sort of language, it seemed that what happens when you execute a function, you evaluate the arguments, and then you add the arguments to the environment, and then you execute the body of the function. And here it seems like parameters in the environment are sort of separated, right?
So let's be clear. So and again, we're over time, so I will just have to come back to this and do this next time. This is the evaluation of an FN form. It is not an evaluation of a function application. Right? This is function application down here. This is function application.
Mm-hmm.
Okay, and when you evaluate a function, this is exactly what you normally do. You evaluate the operand in the environment to get a procedure, right? And then for all the arguments, you evaluate the argument in the current environment, right, to get the values. And then you call the procedure on the values, right? Right. But the point is that this proc is going to be overloaded, and that's where things get hairy, right? So if you generate a procedure of the lambda type, this is the lambda expression, or in our case, fn/lambda. A procedure is a callable thing, right? And it takes some arguments, obviously in itself, right? And what does this procedure do? And this is the metacircular evaluation thing that's crazy, right? It calls eval on its body in an environment which is an extension of the environment in which the procedure was defined, in which the parameters are also bound to the values of the arguments.
Mm-hmm.
So, and just to be clear, this eval right here, this eval is this function.
Yeah.
So the critical thing is that anonymous functions capture the environment in which they're defined. And then when you evaluate the body of a function, you clearly have to be able to refer to variable values that were in scope at the time of function definition. And that's where the concept of closure, not the language closure, although that now you understand why there's this beautiful fun, but the concept of a closure comes into play. A function closes over not only its arguments, but its environment. And this is how continuations capture what has happened before in the CPS transformed version of things. So yeah, we'll come back and do that again. We'll do it both in Lisp style and in Python style, but that's pretty much it, right? There's a very simple language. It has an incredibly small number of forms. This is the new form, and it replaces everything. But if you haven't implemented this before, look at Lisp before next time, please, because and SICP before next lecture, because we really need to get through this quickly, because I want to talk about sequential Monte Carlo, which is even trippier. But focus here and here. Of course, it doesn't hurt to focus it on how you look up variables in an environment. The last thing that you need to recognize is that when you're trying to resolve the value of a variable, you will look up the value of a variable in a nested set of environments. In other words, you'll ascend the stack trace, basically. Okay, so we'll leave it there. I'm sorry to have run long for anybody who needed to go. And I see, Amin, you have your hand up. I will answer questions, but I just want to say that that's it. So yeah.
Yeah, so why do you do things in Lisp too? I feel like I'm missing something.
Why do we do things in Lisp?
Yeah,
is that a serious
example,
question at this point?
I mean, you write the evaluation for importance sampling in Lisp functional style, didn't you?
Yes. What's the question?
Your slides before.
Here?
No.
Or here? or here.
And you were talking about important sampling implementation.
Here?
Here, yeah. You wrote a evaluation in Lisp style. Why? I feel like I'm missing something. Are we supposed to write anything in Lisp?
No, you don't have to write anything in Lisp. No, this is stuff from the book, so that people who read the book and invest the time in actually looking at the book and understand what a function is in the book notation. We don't switch from the implementing language to the implemented language. They're all the same. We assume that the underlying language has the capacity to write functions. Doesn't matter if it's Lisp or Python or C or whatever.
Thank you.
I also have a question. So like I think that I understand like why you want to do this capturing of like the environment for each function so that you deal with like the recursion. But like in this continuous thing where we always call like the continuation function with like whatever we have so far.
Okay,
I don't see where we call eval.
Can I stop you for just a second? Right. So you are not going to see continuation passing style form code.
Okay.
You're not going to write a continuation passing style thing at all. That was a little segue, quite a long segue, 15 minutes, to say if you want a high performance probabilistic programming language, you want to do continuation passing style and you want to be able to capture continuations. Okay. That is not what's happening, right? The way you capture continuations in an interpreter is that you have an explicit environment. And somebody, I remember, I'm gonna unfortunately, I believe that is the person who looks like Bane today, so we won't be able to see the reaction. Somebody at some point used a lot of deep copying in some of the homework. So in order to capture the environment or like do a continuation style thing here, or rather multiply continue the program from the same execution point, you need to be able to fork the environment. You need to be able to branch the environment in a way that does not let any future executions mess with values in the environment. So
is this like the immutability thing?
This is what?
The immutability.
This is now Payman's point about immutable data structures. This is the first time that the immutable data structures show up, i.e. if you write your environment in homework 5 using immutable data structures, you will have a much, much, much nicer time in homework 6. Because in homework 6, you need to branch your evaluator state. And that's the same way of saying this is a continuation. I'm going to say, okay, the continuation is explicit. You have an evaluator. You can just go forward multiple times if you want to, right? But when you do that, you run the risk of overwriting your environment because Python, unfortunately, has mutable state, right?
Only for some data structures.
For all data structures, almost.
Well, I think that strings are immutable, but yeah, that doesn't really matter because we don't really use it.
Okay, fine. Yes, exactly. Yeah, true. Fine.
Okay, so still like in the continuation part, like do we do eval anywhere there? Because like my problem with this continuation style of writing down programs is it seems like you're just going down deeper and deeper and deeper. And I don't see when you start like popping stuff back. Like in the recursion, you go down deep and then you start like popping results, right? But in the continuation, it seems like it's just going down and never ends.
That's correct. But the fun thing is, because the continuation functions. Okay, let me get this right. I actually have to think about this just a second. Let me make sure I get this right. Yeah, I mean the interface, the fixed point, however you want to say it, is that the continuation function, when you call it, is the rest of the computation. It has no there is no dependency, you know, like it, that's it. That's the continuation, right? Any there again, you don't. I don't want to think about. I really don't want to think about stack machines here, and I'm going to get it all screwed up. But it is possible to what is called trampoline. The calls in a CPS transformed program, such that there is no growth of the stack.
Okay, this doesn't help me to understand what's going on, because like the continuation, like you pass functions, but what, like then I don't see what happens with like the recursive calls. Like the function, the continuation function, it's gonna be the function itself. So where does it eval? Sort of. I don't. That's really unclear to me.
If you're asking where does, if you're writing an interpreter, so if you're writing an interpreter for, if you take, so your interpreter will be able to process continuation passing style code. No problem.
Mm-hmm.
Okay.
Okay.
So that's the first thing, right? So if you decide to write things in continuation, do a continuation passing style transformation, your interpreter will still work. And what it will do is it will encounter, you know, an FN form, right? Mm-hmm. So the continuation passing style function will have as part of its body an anonymous function. But when you eval that function captures the environment.
Mm-hmm.
And then you call that function then you apply that function when you call the continuation. Right? So there's a capture environment, call the function, 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 right? So the eval of the continuation function captures the environment, and then when you apply that function, you use the captured environment. That's what happens. So you're always like, you have a programming instruction, you have a program that has a continuation function at the end. Mm-hmm. That's an anonymous function. When you eval the expression for an anonymous function, it creates a procedure. That procedure captures the environment.
Oh, okay. I still, maybe you don't understand my question correctly, but
that's entirely possible. Yeah.
Yeah. So like the continuation function of a recursive function that's calling itself, it should be the function itself, right? Or this is not entirely true.
Yes, that's true.
Okay, then this goes into like infinite loop, where you just evaluate like the next local environment and the next local environment and the next local environment.
No,
like,
no. It doesn't go into an infinite loop, because there's always provided that it halts. There's always a branch, and at the very end, when you hit that branch, you will call the continuation passed to the recursive procedure.
Okay. Oh, okay. So like the function, it can have different continuation functions. Just like in the recursive functions, you can, like, the continuation function can be different. Then is that it?
So there's, when you have conditionals, if you want, afterwards we can go through the.
Okay.
I can open up the book and share the screen and talk about the continuation passing style. But if you've not encountered it before, it's wildly confusing. And my advice to you is that the only way really to understand it is to do some examples.
Okay.
In particular, you're talking about the base cases of a recursion, which always involve some sort of branching statement, an if statement, and the if statement can. An if statement will call different continuations based on the continuation function of an if expression will construct
Okay. I see.
an anonymous function that for the predicate which calls a continuation which has an if expression in it.
Okay. Yeah. No. I think that this kind of solves my problem in my head.
Okay.
But yeah.
I think I understand where your problem was.
Yeah.
Yeah.
Yeah. Sorry if I took too much time.
No, that's great. Yeah. Another question, Immune, or you're just showing off your awesome hair, making me feel bad for not having any?
I'm going to lose my hair soon, I think.
Well, it's awesome now, so yeah. Any other questions? Yeah, is that a buy or is that a bot? You have a question, Ryan? Buy?
No, just buy.
Oh man, I thought you were going to talk. All right.
Great lecture, though. Thanks.
Oh yeah. All right. All right. If there's no other questions, we'll see you on Tuesday. Do please look at
I have a question.
Okay. Yeah. Do please look at the evaluator and get ready for sequential Monte Carlo. It's fun.
Yes, for the evaluator, when we are creating Lambda functions, I assumed before that we are going to need stacks for handling environment variables, but seems like we don't use stacks here to handle environment variables. So, but why do we have outer and self in the environment? Like, why don't we merge the parameters of the environments?
You could, but then you would definitely not have try it and find out what happens. So what will happen is if you have variables that have the same name.
Yeah, they're really problematic. Yeah.
So not only will you have a problem, but if you merge them, then the question is, when if you overwrite, so we have functional semantics, we have pure semantics in the language. So if you use the same variable name before a function definition and then after a function definition, and you merge the data structures, then which version of the variable are you looking at?
Yeah, right. Got it. Thank you.
Yep. More questions? More comments? No, everybody's ready to go. All right. Cheers.